All right, and welcome back. So today we'll change the topic a little bit. We'll be looking at waves, specifically mechanical waves. So there's several different waves, like the one which is the electromagnetic wave. There's mechanical waves. There's gravitational waves that you might have heard recently in the recent years, like the two black holes, right? The first gravitational waves been detected. But um, the focus here will be on mechanical waves. Okay, so the definition of wave is, in general, is a disturbance that propagates from the place it was created. Okay, so just like water waves that you guys are very familiar with. So for mechanical waves, there are two types of mechanical waves. One is called the transverse mechanical waves, and then the other one is they call the longitudinal wave. But first, talk about in general waves. For waves that I just mentioned, three types of waves: mechanical waves, electromagnetic waves, and matter wave, which as one of them is the gravitational waves. Okay. Um, so for mechanical waves, they are governed by Newton's laws and requires a median. Now for the other two waves, they do not. Okay, so electromagnetic wave can propagate in vacuum. Gravitational waves can also propagate in vacuum. Okay, but for mechanical waves, it needs median. So two main medians. One is through the solid, like the string, the standing waves in the string, through air. Air is not vacuum. There's actually a lot of air molecules surrounding us. Okay, so air molecules, they are acting as the median for the sound wave in that sense. So two types of mechanical waves, as I just mentioned. Transverse wave, that means as the wave propagates, the median also vibrate up and down, which is in the direction perpendicular to the direction of wave's propagation. Okay, so if medium vibrates perpendicular to the direction of the wave propagation, it's called transverse wave. Longitudinal waves is where the median oscillates along the direction of the wave's propagation. So wave propagates in the horizontal way, median here propagate back and forth. Okay, that's in the along the same direction of the wave's propagation, but not propagate along with the wave. Okay, so it just vibrate back and forth, but in that direction, in the horizontal direction. All right, so if you guys go surfing, right, then if a wave comes in, you are part of the ocean. So the water in the ocean is the median of the ocean waves. Okay. So the question to ask, do you travel along with the wave in the same direction or not? So wave goes in the horizontal direction, right? So if you are on the ocean, you go up and down, right? And a little bit from in the wave direction, but you don't go along with the wave, right? So the answer is no, you don't travel along with the wave in the direction. Or if you go to a sporting event, right? So one of the famous thing people do together is called waves, right? So you jump from your seat up and then sit down back, right? So you don't propagate as the wave propagate from to your neighbors, right? You hopefully you don't jump into your neighbor's seat, okay? So that's put in that way. All right. So for a wave, so there's propagation of waves. That means the wave travels. So then the speed of wave, that's one of the quantities will be our particular interest. And also because it's a wave, so that means it kind of repeat itself periodically, right? So in this case, the medium vibration of median repeat itself. So going back and forth, okay? And as the wave propagates, the peak or the valley of the vibrational medium actually also propagates in the direction, positional direction, or in the positional axis, okay, say to the horizontal in that sense. All right, so the period that the median oscillates is called the period of wave. And as the wave propagates, the time it takes to Yeah, that's the period, right? So then in the time of period, the distance, the peak travels or the wave travels is called the wavelength. Okay, so there's a wavelength, there's period, and then there's amplitude. The maximum displacement of medium from its equilibrium point is called the amplitude. Okay, so A. So there are four quantities here: the period, the wavelength, the amplitude, and the speed. Okay, of the waves. So for the speed of wave is equal to the distance traveled, right, over one period. So lambda over t, or we can say lambda times f, because 1 over t is called the frequency. So lambda times frequency. Okay, let's take a look on the first example here. If you were to shake the end of a taut spring up and down 10 times a second, what will be the frequency and the period of the sinusoidal wave produced on the spring? Can we just say sine wave? Yeah. All right. So let's take a look on this guy. So you shake it up and down 10 times. So that means the frequency, or 10 times in 1 second. That's the frequency, right? So that's how fast you do that. F equal to 10 hertz then. So it's asking you what's the frequency. Okay, we got it. Okay, so that's the frequency. And it says the period. So the period will be 1 over frequency, right? T will be 1 over F. So 0.1 second. All right, and then that's it on this one, okay? So let's go back. Pretty simple. Share the screen. Switch my camera. All right, a second one. It says a sine transverse wave. Okay, sorry, I have to switch back to the my work paper. So on this one it says a sine transverse wave has a wavelength of 2.8. So wavelength equal to 2.8 meters. It takes 0.10 second for the portion of spring at the position X to move from maximum position of Y equal to 0. So that's the amplitude, the maximum position, to the equilibrium Y equal to 0. What's the period, frequency, and speed of wave? Okay, so let's take a look on it. It says it moves from Y equal to maximum of, so let's say a sine function. Okay, so it could be a cosine function. Both are as sinusoidal function. Okay, so it says from maximum to minimum, the time it takes here, t is equal to 0.10 seconds. So if you look at this, this is a quarter of the whole wave. Okay, so you can divide it into 4 sections. Each one is 1 quarter. So okay, then we know that in this case, then t will be 4 times of that. So 0.4 seconds then. Okay. So the period and the frequency now again will be 1 over t. That should be 1 over 0.4 second. That should be 2.5 hertz. Okay, so that's your frequency and the speed. Speed is equal to frequency or lambda times frequency. So we can do that. Or lambda over period. Either way, that should be giving you. They should be giving the same answer. 2.80 meters times 2.5 hertz. So that gives you 7 meters per second as the speed of the wave. Oh, sorry, it wasn't showing up. Or was it? Okay, so 7 meters per second. Okay, let's go back to the slide. Now let's switch back the camera. Okay. Now let's take a look on longitudinal wave. Okay, so the displacement is along the direction of wave motion. Displacement are the median. Okay, so in that case, so back and forth, or in the slinky, if you generate a wave that you go back and forth, then the slinky vibrates back and forth. Okay, in the direction of the motion of the wave. Mathematically, so when the wave propagates, this is what it looks like, right? If you create a wave, then it propagates to the right. Okay, so you can see the position of the median y, okay, depends on where you are standing at, right? So so for y at this x, right, then it's different from y equal to 0 here to there or there. Okay, so it depends on that. It also depends on the time. So in the second time instant, right, this wave propagating here. Okay, so the position of the median y, it depends on the position and then also a function of time t. Okay, and back in physics 1, we talk about oscillation. So when we have oscillation, right, so then you kind of generate the position of the median goes back and forth, right? So we use actually a sine function or cosine function. So for the position, so if we use a cosine function, okay, then it's a cosine omega t. So omega is related to the frequency, the angular frequency. Okay, so omega is equal to 2 pi times f, or 2 pi divided by period times t. That would be the omega. Okay, we can also use a sine function. Okay, so they are the same. So then to model the wave function, so then it should be a function of sine of the position, and then it should be a function of the time t. Okay, so using a sine function, you will be able to do that or cosine function. Okay, so you can the propagation of that, the wave. All right. So in terms of the wavelengths, so in this case, if you have a sine function, right, sine of theta, so it vibrates like that. If we have a y, which is a sine function, and that's in the in terms of position, okay, a sine function similar to that. So let's do some substitution. So for the angle here, this is the x, right? So angle over x. The period here is 2 pi, in this case is lambda. So then theta over x is equal to 2 pi over lambda. So theta is equal to 2 pi lambda x, okay? So for the sine function, y of theta as a sine function, then y of x then will becomes there will be an amplitude not necessarily equal to 1, but a sine of, so replacing theta with this guy 2 pi over lambda x. Okay, so then wave function become a sine of 2 pi over lambda times x. And it also propagates as time t, right? So minus of v times t in that sense, because next time it will be here, right? So then it's the same as if wave propagate to the right, to the left, to the right, right? So you do minus of omega of minus vt, because this then recovers original wave in that sense. Okay, and y should be equal to x plus v x if it propagates to the left. Okay, so propagating to the right is minus vt, propagating to the left is to the plus vt. Okay, so then the wave function as a function of position x as well as a function of time t is equal to the amplitude sine of 2 pi lambda. Now x is either x minus vt or x plus vt. For minus vt, the wave propagates to the right. For plus vt, it propagates to the right, left. Okay, and you can distribute this into the equation. Okay, so then it becomes, if you distribute that into the equation or the parentheses here, it becomes 2 pi lambda x and then minus 2 pi v over lambda. Okay, so then we define 2 pi over lambda to be k, called wavelengths. Okay, and then this term, let's take a look on this term, will be this guy. If you multiplied by, so if the v is written as the lambda over t, right? So then lambda cancels, then becomes 2 pi over t, and we call this as omega, right? We learned that. So that's the angular frequency there, okay? So then it becomes a sine of kx minus omega t then, okay? So a sine of kx minus omega t, all plus f is propagating to the left, okay? Where v is equal to lambda over t, or you can see this here. So if you do 2 pi over t, that will be omega. Lambda over 2 pi, that will be k. Okay, so you can also be calculating that as omega over k. So v can be also calculated using omega over k. Now, in general, you probably don't have a exactly sine or cosine function. There's a phase shift or initial phase, right? As we mentioned in physics one. So then the x as a function of omega cosine or sine, there's a initial phase theta. Okay, so in this case, you can add also the initial phase for the wave function. Okay, so then in general from a sine of kx either plus or minus omega t plus 5 for the initial phase of the wave function. All right, so let's take a look on the example here. This one, it says, consider the wave function. Okay, so this guy wave function is given a y xt equals to 3.00 centimeter. That's the amplitude, that's A, okay? Sine of 0.4 meters inverse. So this is your K times X plus your omega, 2.00 second inverse. This is your omega, K, omega times T. And then plus the initial phase of that guy. Okay, so this is phi, initial phi. That's asking you period, okay? Period is related to the frequency. If we have frequency, you can calculate, okay, for angular frequency. And wavelength is related to the wave number. Speed, once we have frequency and wave, we can calculate speed, right? And then initial phase, okay, initial phase is that guy. All right. So now this case is plus, so it just means this wave is propagating to the left, okay? In that sense. So K equals to 2 pi over lambda, omega equal to 2 pi f. Okay, so then from here, f, or let's do this, because this could be also equal to 2 pi divided by t. Okay, so then t is equal to 2 pi over omega. Okay, so 2 pi over 2.00 second inverse, that will be pi seconds. Okay, or 3.14 seconds, maybe, if you want to call it that way. Okay. From here, lambda then it be equal to 2 pi over k. So 2 pi over 0.4. Okay, so that would be 5 pi meters in meters. Okay. Okay. So then v would be lambda over t would be 5 pi in meters divided by a pi in seconds. So 5.0 meters per second. Okay. Initial phase is pi over 10 as shown. Okay. All right. So going back to the slide. So we have the position, the wave function as a function of the position and then t, okay? So this is the displacement of the median as a function of velocity and acceleration. Minus means it's propagating to the left, to the right. If it's plus means propagating to the right, okay? So then the velocity of the median as a function of t, you can do partial derivative of the position over dt because there are two variables, so we can do partial derivative, just the same as derivative, okay? So a sine function becomes cosine function minus a cosine, and then in here, t is a variable, so minus omega will come out. Or sine becomes just positive cosine, sorry. And then minus omega comes out, so minus a omega cosine of the argument in the parentheses, which this a times omega is the maximum velocity in the y direction because the median is vibrating in the y direction, okay? Acceleration then can be calculated by doing partial derivative of the velocity over t. Okay, so then again, doing derivative to this. One more time, minus a omega square sine of the function. So minus a y max will be this a omega square. Okay, so once you have your wave function, velocity and acceleration can also be calculated. All right. So let's take a look on this example here. It says the wave function for a harmonic wave on the stream is yxt equal to amplitude 1.00 millimeter sine of kx plus omega t. Now, no initial phase or initial phase is 0. In what direction is this wave travel? So it's plus omega t means travel to the left, right? Or minus x direction. And what's the wave speed? So what's the speed? Find the wavelength frequency and period of the wave and see what's the maximum speed at any given point on the string. Let's take a look. All right, we'll first write down the wave equation that's given to us. Yxt equal to 1.00 millimeter sine of 62.8 meters inverse times x plus 314 second inverse times t. Okay, so this is k, this is my omega. So a to the left or minus x direction. That's the propagation of the wave. And then v equals to lambda over t. So we need to find out lambda and t just as what we did earlier. Okay, so for lambda, we do k equal to 2 pi over lambda. So then lambda equal to 2 pi over k. 2 pi over 62.8 meters inverse. That gives you 0.1 meters. Okay, so that's the wavelength. The frequency, we do omega equal to 2 pi f in this case. Okay, and frequency equals to omega over 2 pi. 314 inverse over 2 pi. So that's 50 hertz. Okay. So then this is equal to 0.10 meters over 50 hertz, which is 0.002 meters per second, okay, or 2.0 millimeters per second. Okay, and the period, so t then equals to 1 over f will be 1 over 50 hertz, 0.02 seconds. Okay. See what's the maximum speed at any given point. So the maximum speed you can do a omega. Okay, so a would be 1.00 10 to the minus 3 meters. Omega is 314 second inverse, so 0.314 meters per second, the maximum speed. Okay. All right. So the acceleration of the median, we do double derivative, in this case, double partial derivative because there are two variables again, x and t being variables. So then that's as a result, it's minus a omega squared sine of kx minus omega t plus 5. Now, if we look at the slope of the wave function, then we do partial y over partial x, okay? And then for the curvature of the slope, you do double derivative of y over double derivative of x, okay? So in that sense, you get then this guy here, minus of ak squared sine, okay? The same sign if you compare the two, but different amplitudes in top or in the front. So v equal to lambda over t. So in this case, then if you do the ratio of this to that, okay, so then that becomes v squared. So then this double derivative of this wave function with t is equal to then 1 over v double derivative of the wave function with respect to x, okay? So then that is the wave equation, okay? So that will satisfy that. Okay, so then on the other hand, if you have wave equation, then one of the solution will be sine function or cosine function. Okay, that's on that. I think we'll just stop here for today, and then we'll come back next time. Okay, see you guys. Bye.